Hello everyone, and welcome back to ENL 582, Modeling and Control of Electric Machines and Drives. So last time we started talking about the construction of a simple machine. Okay, so we call this just a simple machine because we're talking about principles that can be applied to any kind of machine actually. But let me be more specific here, and I'm gonna call this not just a simple machine, but a simple DC machine. Okay. What I mean by DC machine, we'll be talking about this in a minute, but the idea is just the machines in general are just like we said before multiple of times, it's just the machine is an energy converter. Okay, that's a device that converts electric energy to a mechanical energy, and that's called a motor. Or it's a device that converts mechanical energy into electric energy, and that's a generator. Okay, but how the machine do this conversion, that is different from various types of machines. Okay, the idea is just how this conversion happens. So you have various types of machines. We'll be studying mainly the main three types of machines: DC machines, synchronous machines, and induction machines. Okay, the basic principles applies to each one of them. If you want to make a generator, then you simply need to have a coil like this that is moved inside a magnetic field, cutting this magnetic field, and then electric voltage will be induced in this coil, and now you have a generator. So you need an external mechanical force to rotate your coil inside this magnetic field, and you will have electricity. If you want to build a motor, then you need to pass electric current into this coil while cutting the magnetic field, and now you will have rotation. You will have induced torque to rotate these coils inside the magnetic field, and we'll be talking about this in a minute. Okay, so any kind of a generator apply the same principle, any kind of a motor apply the same principle. Okay, but there is different design aspects between different kind of machines to achieve the same purpose. Okay, so you can have DC generator, you can have induction generator, you can have synchronous generator, and much more. They are all generators, they are all applying the same principle of this, but they have, each machine or each type of machine had its unique way of doing this. They are different constructions, they have different theory of operation, and we'll be studying them all. The same idea with motors. You will have DC motors, synchronous motors, induction motors. They are all motors again, they are all doing the same principle in a way or another, but each one of them has unique details that related to this kind of a machine. Okay guys, so we'll be start talking about DC machines because it's some way more simple just to study the principles of machine with it, and then we'll be move forward to study the more important one, the synchronous machines and induction machines, because those two kinds of machines you will be facing a lot in your industrial life or just facing industrial applications. Okay, so like we said last time, if you want to build a small or a simple DC generator, okay, so this is the same principle here. You're talking about just having a magnetic field source like we said last time. There's a north pole and a south pole. This can be a permanent magnet, just pieces of stone that's permanent magnets, while it's from nature or manufactured, to give you a north pole and another one to give you a south pole. Or you can have them by have electric magnets, just having coils. Okay, so you just trap a coil and apply electricity to it, and this coil will be just act like a magnet. Okay, and you have your coil inside this magnetic field. Okay, if you apply an external force to rotate this coil inside this magnetic field to cut it, a certain amount of voltage will be induced in this coil. Okay, this certain amount of voltage can be quantified using this Faraday's equation, the famous one, E equals V, which is the linear velocity of this coil. We said it have to rotate, cross B, which is the magnetic flux density, and the result is dot product with L, which is the conductor length. Okay guys, so this gives you all the information. If you want to generate electricity, if you have an electric voltage induced, you need to have a piece of wire that have a length L. Okay, it will be much efficient if you wrap it into a coil like we do, and you have to move it with a velocity V inside a magnetic field with density B. If you apply those three requirements, now you will have electric voltage induced in this coil, and you have your small generator. We talked in detail last time about how to do this. The idea is, if you want to calculate this, you want to just have your coil, and we just have this coil just having three sides like this, side 1, 2, and 3, like we told. So this side and this side and this side, we call this 1, and this 2, and this 3. Okay, and we have just calculated the induced voltage in each one of them, and we said that from this configuration, like here, the velocity v vector and the magnetic flux density vector B and L, which is the length of the conductor, they are all vectors and they are all perpendicular to each other. You have a 90 degrees angle between all of them. They are all perpendicular in space, and that means you don't bother with all the angles between them. This magnitude of energy of induced voltage you will having will be simply VBL. You multiply the linear velocity by magnetic flux density B by the length of the conductor L, and that gives you the magnitude of the induced voltage you want to calculate. If you want to know the direction of it, where the negative and the positive of it, because it's just a voltage applied, okay, you just follow the regular right hand rule of just cross product, because you have cross product of V cross B to get the magnitude of this dot product with L. And this is what we did last time, and we just figure out this. In the first one you will have a negative here and a positive here, and with 2 you have a negative on the top and positive on the bottom, and on 3 it's 0 because it is just parallel to the direction of flux, because if you just look over there, the direction of flux is just like this, that is B. So this conductor 3 is just parallel to the flux, though you will not have any induced voltage in it, because like we said last time, this particular one, the V cross B, will give you a vector that will be perpendicular to L, and now if you want to get the dot product of them, it will give you 0. So that's why we call this end winding or overhang last lecture, because it's not a part of the energy conversion process, because you will not have induced voltage in it. Okay, but the two coil sides 1 and 2, they're the ones they will have induced voltages, and if you apply Kirchhoff voltage law to them to find the total one, because the total induced voltage in this whole turn will be just E1 plus E2 plus E3 even, but E3 is equal 0, so it will be mainly E1 plus E2, and it will be 2 VBL, like Kirchhoff voltage law, like this. Okay guys, and it will have the total ones, you will have a negative here and a positive here. Okay, like we said, that's why if you apply this to an external load R, the current will be moving in this direction, okay, like a generator. So that's the thing we'll be talking about last time. Let's just stress more on this and see what will happen about this. Okay, so we're talking that in this coil, we are just rotating the coil like this. That is the direction of the angular speed omega, okay, anti-clockwise. So in this position like this, you will have 1 here and 2 here in this position. Let us see what will happen. So I'm gonna say this, let me just draw it like that. Okay, it will be much easier to deal with. So that is the south and that is the north, and here is your rotor cylinder, and there was the side 1, and here is the side 2. Okay guys, and you know that that is the direction of rotation. That means from here you will have this velocity V goes up, and that means this velocity goes down, like we said last time. Okay, excuse me. And in this particular position, like we calculated last time, so if you want to E coil from here, it will be just let me say not E coil, just E turn, like we said last time, just 1 turn. So if you want it for the whole coil, we will multiply by the number of turns in this coil, simple as this. But the E turn here is basically 2 VBL, like we said. Okay, but for the total polarity of it, it will be negative with 1 and positive with 2, like we just explained right here before. Okay, guys? If you apply the same principle, just look here. Now, what will be the new position of all of this? Because it just keeps rotating, yeah? So you still rotating anti-clockwise like this. So that is your cylinder. And I will keep tracking this. So the 1 will be here and the 2 will be down there because it's rotating around itself, yes? In this position, can we calculate the E turn again? The total induced voltage in the whole turn like we said last time? Yeah, we can do it. The same principle. But if you look over here, these coiled sides are not facing magnetic fields because they're just facing empty space over here. Yeah? So the magnetic field just coming like this from these north to south, like this. So in these positions, 1 and 2 are not really facing magnetic fields. So there will no be induced voltage in here. So in this position, while it's rotating, you will not have voltage induced in the coil. Okay, guys? So let's keep moving to the next position. Again, we're talking about something that rotates, yeah? Remember, the north and south here, they are representing the pole that is attached to the stator. The stator does not rotate anywhere. So the S and N will be keeping fixed position. They are not rotating because the rotor is the thing that rotates, okay? So your rotor is the one that is rotating like this. And this is rotating also. Everyone is rotating anti-clockwise like that, okay? But in this position, like here, now, after it keeps rotating, 1 will be here, the side 1, and side 2 will be there. Okay, guys? If you just look like this here, you will say that it will be the same idea. So the same coil, this coil, is just rotating around itself like this. So this guy is rotating. Okay? So coil 1 here, or just the one in the right hand side, and that's one having V going up. Okay? And the same idea, the coil side V, that is the one, sorry, the coil side 2 that have the velocity vector goes down. Okay? But here, if you see, now 2 have the velocity vector going up, and 1 having the velocity vector going down. Okay? That is the totally opposite ways of the position number 1 here. Okay, guys? So, doing the same idea, you will be having this. That's the total polarity of the induced voltage. 2 will be negative and 1 will be positive. Okay? They have the same magnitude. So, E turn also equal to VBL. Okay, guys? It is the same idea. Because, yeah, if you want to calculate the same thing, that is the side 2 here. The V will be going up, and the B will be just this direction. And the L is just going into the page. If you apply the same principles of the right-hand rule, you will find induced voltages like negative in here and positive on the other side. Okay, guys? Okay. So that is the idea we'll be talking about here. So if you're looking at position 1, let me say this position 1, and this position 2, and this position 3. So in position 1, the coil side 1 has negative sign, but in position 3, the coil side 1 has a positive sign. It changed polarity. Okay, guys? So when it's facing one pole, the south pole, it's a certain polarity, negative or positive. When it's just switching polarity on the other side, it will be positive. Okay? So if I want to just have the induced voltage coming here, okay, and I just want to plot it with the position like this, because we're talking about a position that's talking. So you will find it positive in some positions. So if I'm talking about the E of the coil side 2, for example here. So in position 1, that is position 1, it was positive. Look here. So this is 2, and that is a positive sign here. Okay? But what are you talking about in position 2? In position 2, they are 0. So it's position 2 here, and that is 0. That is position 2. What about position 3? In position 3, coil side 2 has a negative sign. So I will go down here to be a negative sign. Okay, guys? So that will look like the voltage you can have from each coil side, from those guys. Yeah? What is the problem with this kind of voltage you've seen here? So it has two problems we're gonna talk about. So the first one, this period, you having this 0 voltage period. 0 voltage. And we don't like this, because that means we're not making the most of our machine. Okay, guys? That means we are not making the most of our machine. We need to just take out this 0 voltage because we need to have voltage value at each time. Okay? So we'll try to get this voltage period out, or to minimize it as much as we can. So this thing, we don't want to see it. The other thing is just looking like here, this voltage is AC. Remember we're talking about AC versus DC? Because you have a period that is positive and a period that's negative. And if we are trying to build a DC machine, like we said, we are talking here about a simple DC machine. That means the voltage we're trying to get out of this machine, we want it to be DC. So we don't like this to be AC. So those two problems we want to fix. We want to get rid of this 0 voltage period as much as we can. And we want to convert this voltage, rather than having sometimes it's positive, sometimes it's negative. We want it to be all the time positive or all the time negative. Fixed. There's no polarity here, but sorry, it's not alternating, because we want it to be DC. Okay? Because we are building a machine to be DC. Okay, guys? So how we'll do this, we'll get back to this in a minute. But before getting back to this, let me see what we can do if we are trying about a motor mode. Okay? So we built now a simple, small DC generator. Okay? What if we want to have a simple DC motor? That is the other type of electric machines we are trying to deal with. Okay, guys? So we are talking about a motor. This motor is just the device that have input electrical or electric energy or electric power, whatever you mean, and its output will be mechanical energy. In more way, that is rotation. Remember, this is very much good. So in the generator, we apply rotation from a mechanical source. We rotate the rotor by an external mean. We force the rotor to rotate in a certain direction we want it to go in. Okay, guys? But if you're talking about a motor, you're not applying any mechanical rotation to the rotor. You want the rotor to rotate from its own, because that is the output you want. That wants this motor or this device to rotate once it's plugged into an electrical source. Okay? Let's see how this can work. Okay? So we will have our same construction, because you will know this. Okay, in this kind of machines, the same construction can be a generator or a motor. It depends on just the connection. Okay, so it is the same device can be working a motor or a generator. If you applied a mechanical force or mechanical torque from outside to force the rotor to rotate in a certain way, and you apply a magnetic field, now it's a generator. If you have these same coils but applied an electric source from the outside to push electricity into the coils while cutting the magnetic field, it will start rotating. So it is the same construction, the same device, can be working either ways. It depends on what input you are applying and what output you are expecting. Okay, guys. So I will get the same photo we are just playing with. Okay, so we said, so it is again the same construction. Okay, but now rather than having the plane with the last time, it is the same coil we're talking about here, and it's the same idea. Now it is the coil side 1 and the coil side 2 and everything. Okay, but now I'm gonna attach this to an external DC source. Why DC? Because we're talking about a DC motor. Okay, so rather than rotating this coil inside the magnetic field and expecting to have induced voltage in it, now I'm pushing voltage to it from an external electric source. Okay, so rather than like this, you will have current moving, electric current through here, so you have current moving through the coil. So the current will be moving inside the coil like this, and coming back from here. Okay, guys? And you still have the magnetic flux going from the North Pole to the South Pole like that. So we are now having everything we need to have a motor. We need electric current to move through a coil while cutting a magnetic field. So now we have everything in hand to have a motor, okay? But how this really works? Again, we're trying to model this to quantify everything. So like we have the V cross B dot L to have the induced voltage from the generator equation, we have also a motor equation. It says that the force equals I times L cross B. Okay, what is this? That is F, which is the mechanical force in newtons. Okay, let me just have another color to make it visible for you. So F is the mechanical force, the mechanical force created. The output mechanical force that will be have it will equal the I, which is the electric current in amperes that's moving through your coil, and L again is the conductor or wire length in meters, and B again is the magnetic flux density in Teslas. Okay, so it is the same principle. We're gonna say it out loud. Okay, if we pass a current, or let me say it just to make it visible, an electric current I, okay, in a wire or into a wire with length L while cutting a magnetic field with density B, okay, what will happen? A force, or let me say it again, a mechanical force F will be developed on this wire or conductor. Okay, guys? Again, the same idea we'll be talking about how to find everything. It will be the same idea like this. Okay, guys? So that is how to quantify everything like this. Okay, so again, the length L will be just going with the direction of the conductor itself. Okay, the flux density B coming from the north to the south like this. So the B is just perpendicular to the L, and now we get rid of all the thing, and I is basically a scalar, not a vector. So from your electromagnetic courses before, electromagnetic fields, you know that the electric current is a scalar, not a vector. So L cross B will give you just a certain vector, okay? And that is the whole point of this. If you want the direction of this, of the force that will be applied to this, or that will be induced over this coil, it will have this certain direction of the vector coming from L cross P, again coming from the right hand side rule. Okay, apply your thumb with L and your flux density vector, the index finger with B, and your middle finger will give you the direction of the force. If you do this with that, so look with me on this. So that is on coil side 1, that is where L goes in, okay, and that is B coming from here. If you apply this, it will give you F going down here, okay? So it will have induced force 1 going down, okay? The same idea applies to the coil side 2, okay? Did the same idea here. L going down like this, or just coming from outside the page like this, okay? And you have B in this direction. You will have F2 going up like this, okay? So to make it more visible, now I'm gonna make it in 2D. So again, that is your south, and that is your north, and here's the rotor, okay? The same idea. So here's 1 and here's 2, okay? So this will have induced force 1 like this, and this will have induced force 2 like this, okay? So from this will start rotating, if you can see, clockwise like that, because you have certain force F1 induced on 1 and certain force F2 induced on the conductor 2. So this guy will start rotating like this, okay? So that is the magic. That is how this electric current moving into the coil while placed into a magnetic field will result into rotation like this, guys, okay? So you have two forces, each one of them will be applied, F1 and F2 will be applied to the different two sides, side 1 and side 2. This will translate into a rotation, and when rotation comes, you come with the new term, we call it the torque. So the force, guys, is just the mechanical force that acts in linearly, like F1 and F2, they're acting in linear direction, okay? But the torque is basically the force acting on a circular path with radius r, okay? So the vector of this torque is basically r cross the force F, okay? So it is just something that represents, we're talking about force but not acting linearly, it's acting in a rotation. So if you just try to apply it like that, so it's a torque or a force that's acting on a rotation way, okay, guys? So I did the same principle of just having here, that is the south and that is the north, and that is your rotor, okay? So like this here, this radius will be r, there is radius r, okay? And F will be something like the linear ones like this, okay? So if you want to calculate the torque that is applied to this, or just made, or that developed on this, it will be basically r, the radius, cross F, okay, guys? So calculating this will be the same idea. If you want to calculate the torque acting on cross-sectional, or sorry, on coil 1, as called side 1, it will be RLIB, okay? The torque that is on the another one will be RLIB also, okay? So the torque acting in the whole turn will be the summation of them, 2RLIB, because again This conductor, the conductor number 3 here, will be having no torque. The same idea like before when it doesn't have no voltage when you're talking about a generator. Okay, guys? So it is the same principle we are just dealt with before. Okay, guys? But rather than applying an external force to make this thing rotate, and now you have voltage getting, now we are applying electricity to the coil while it's cutting magnetic field, and now a certain force will be just developed on each of the sides, and now you have torque rotating the whole coil while rotating the rotor with it. So we'll be rotating the coils, and the coils placed on the rotor, though the rotor will be start rotating like this. Okay, guys? So it is the same idea now. If we go with the same drawings like before, that is S and N, and now you have the rotor. That was coil side 1, and that is coil side 2. In this position, you will have F1 going down, and here F2 goes up like this. Okay, and the torque we calculated to be 2RLIB, and from this direction like this, it will be working this clockwise. Okay, so it will start rotating clockwise. So let us see what will happen in the next position, because it will now rotate. So 1 will come down here and 2 will be up there. Again, they are not facing magnetic field, and that means the torque in this case will be 0. This is position 2. So this position 1, this position 2, and keep moving to find position 3. That is the south, and that is the north, and that is our rotor. Okay, so I'll keep rotating clockwise like that. Now 1 will come left and 2 will be on the right. Applying the same principles, F2 will now be up and F1 will be down. So the same magnitude of torque will be have 2RLIB, but now from these direction of forces, okay, it will start rotating anti-clockwise. Okay, guys? And now that's not good. That's a problem. Because again, if you trying to just have the torque applied to any kind of them with position, it will be sometime positive, sometime 0, and sometime negative. Because it's sometime clockwise, sometimes 0, sometimes anti-clockwise. That means if you have a motor like this, it will be just sometime moving clockwise, just half cycle clockwise, and coming back anti-clockwise. And that is not really a motor. It can be considered like a toy, because you need to have a continuous rotation in a certain direction, not having just one going and just coming back, one going and just coming back. Okay, so this is not a good thing to have. Again, we don't need to have this. We need to have torque in a certain direction, because we need the motor to keep rotating in a certain direction, not a half cycle clockwise and half cycle anti-clockwise. Okay, so it have almost the same problem that we dealt with before with generators, or generators having AC voltage like that. Okay, so we have those problems, and we will be trying to fix them the next lecture. But right now, other thing I need you to have in mind is how you apply those principles to get a generation of electricity from a simple generator, and a torque production, which means a rotation into the simple motor. They are very important to have in mind, and I hope you get those two principles in mind well. Okay, guys? So I'll stop here today, because I don't want to confuse you more about talking how to fix these problems. Okay, take your time to study this well and apply it once, and we can talk about it in our online meeting, just to see if these principles really apply to your mind well. We need to get this out of the way, because we will keep building on these principles with all kind of machines, with all kind of generators and motors we'll be dealing with. So that the basic principles of how to build a generator or how to build a motor, they are very important like here. Okay, and we'll be keep doing this next time when trying to fix this idea to keep it DC, to build a real DC machine. Okay, so these principles apply to any kind of machines, but next lecture we'll be trying to get this to be really DC, to get DC voltage from the generator and to get continuous rotation for a motor. Okay, anyway, the continuous rotation for a motor we need it for any kind of motors, but the generators, there's AC generators and DC generators, but now we are just focusing on DC generator, how to get DC voltage out of it and how to force this motor to be a continuous rotation while just having DC voltage applied to it. Okay guys, so thanks so much for joining me today. I hope it was an informative lecture and exciting